Chapter 5 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Peter Mosher. The Romance of Modern Electricity by Charles R. Gibson. Chapter 5 How Magnetism is Related to Electricity. A magnet without any iron. A British scientist makes a simple discovery which leads to great things. Some absurd mistakes between magnetic and electrical attraction. How the iron molecule possesses magnetism. Some notable examples of perpetual motion. What happens to the molecule when highly heated? A military analogy. When magnetism and electricity were at first known, there was not supposed to be any connection between them. Then, for a time, they were treated as sister sciences, while now one would feel it more natural to have but one scientific name to distinctly include both. In the preceding chapter, we saw that an electric current flowing in a wire around a piece of iron produced magnetism in the iron. If the iron is withdrawn altogether, it will be found that the coil of copper wire is itself a magnet, as long as the current flows in it. If a light coil of fine insulated copper wire be freely suspended and attached to a battery, it will be found that the coil, with the current passing through it, behaves exactly like an iron magnet. One face of the coil will be attracted by the north pole of a bar magnet, while the other face will be repelled, showing that the coil has a north and a south pole. When a piece of iron is placed inside the coil, the effect is greatly increased. We see that an electric current produces a magnetic field in its neighborhood. Footnote: a magnetic field means a space in which we find magnetic force. End of footnote. A piece of ordinary iron, when placed in this field, becomes a magnet. Therefore, if we possess an electric current, we may produce magnetism in a piece of iron. In the foregoing statement, we see a very close relationship between electricity and magnetism, but this is not all. We shall see that if we have a magnet, we may obtain an electric current in a neighboring coil of wire. It was some 70 years ago that our great British scientist, Michael Faraday, discovered that when a coil of wire was quickly moved between the poles of a magnet, an electric current was set up in the wire at each movement. We have all seen this experiment repeated in those small magneto-electric machines in which one drives a coil of wire round in the magnetic field of a permanent magnet. Such machines are sometimes used for medical purposes, but perhaps more often for amusement. This very simple little experiment of Faraday's in time gave birth to our gigantic dynamos and motors, and when we think of all that these mean, we shall surely not fail to put a true measure of value upon the patient research work of scientific men. Many people make a strange confusion between the meaning of magnetic attraction and the attractive power of an electrified body. I remember a student, when replying to a question as to how one may magnetize a piece of steel, writing down in all seriousness, "Rub it with a piece of silk or flannel," showing that he had confused magnetic attraction with the electrical attraction exhibited by an excited glass rod, etc. Equally absurd was another instance, which happened at the close of a lecture to young people. I had demonstrated electrical attraction by charging a young girl by means of an electrical machine, and then showing her hair attracted to my hand when held over her head. When the lecture was over, I noticed a young electrical engineer-elect place a girl upon the insulated stool, but not in connection with any source of electricity, and then, merely holding a large steel magnet over the child's head, he was quite surprised to find that her hair did not rise to the occasion, he attributing the failure to dampness of the glass legs of the stool. These are extreme cases, but they illustrate a difficulty that cannot exist if one realizes that a magnet attracts only iron to any appreciable extent, whereas an electrified body will attract any substance. The coil of wire carrying an electric current is not an electrified body. One may picture an electrified body as having a charge of electricity at rest in a strained condition, while a body conveying a current has electricity in locomotion. In the molecular theory of magnetism, briefly explained in the preceding chapter, it is obvious that the question as to what magnetism is has only been answered in part. This theory does not go to the root of the matter, as it sets out with the assumption that each molecule of iron is itself a magnet. Where does the molecule's magnetism come from? It is supposed that there is electricity in motion around the atoms of iron, and that each miniature electric current sets up a tiny magnetic field. It will be understood that a molecule is merely a group of atoms. The iron which we see is in reality a great congregation of these invisible molecules. Therefore, the iron has within it a myriad of miniature magnets. When these are all acting unitedly, the lump of iron shows very appreciable signs of magnetism. But when these tiny magnets are all at 6s and 7s, there is no outward sign of magnetism. We may picture a lump of iron, in the latter condition, being placed within a coil of wire in which an electric current is flowing. All the tiny magnets wheel round into the one position, and we say that the iron has become a magnet. It will be observed that the magnetic force was existent already within the iron, and that the influence of the neighboring electric current merely set those tiny forces in order. If we place a piece of gold or silver within the electric coil, we do not get any signs of magnetism in these metals, because they do not contain the myriads of magnetic atoms which we find always in iron. However, we have seen in the preceding chapter that alloys of certain non-magnetic substances, such as copper, manganese, and aluminium, have shown quite respectable signs of magnetism when treated in the same way. There is one point which is worth mentioning. We used to say that iron could be magnetized to a certain extent and no further. This was called the saturation point. The mental picture we formed in those days was that of soaking magnetism into the iron till it could hold no more. Now we have a much more reasonable picture. As the magnetic force resides already within the iron, it is quite clear that we can get a certain degree of magnetism and that we can get no more from the iron, no matter how powerful an electric current we use. It will be clear also why a piece of soft iron, when placed within a coil carrying an electric current, increases the magnetic field. The iron adds to the magnetic field the magnetism which is already locked up within the iron. We shall be able to form a much clearer picture of the nature of magnetism when we come to consider the present ideas concerning electrical phenomena. In the meantime, we are quite able to step out into the world of practical electricity. There we shall find that all the great uses to which electricity has been put are merely applications of the simple phenomena set forth in the preceding chapters. End of Chapter 5.
Chapter 6 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Rick Cordray. The Romance of Modern Electricity by Charles R. Gibson. Chapter 6. How We Came to Have the Telegraph. A Highlander's Amusing Explanation. Man's earliest method of signaling. The first really practical electric telegraph. An American rival which came to stay. An instrument to record the telegraph signals received. Why a complete circuit is required for an electric current. How one wire can now be used. There is an amusing story in connection with the early days of the telegraph, which, whether real or fictitious, will serve to illustrate a point of much importance. One Scottish Highlander is said to have asked another how the telegraph worked, whereupon the second one replied that he didn't understand it, but he thought he could explain it, from which remark one would infer that he had some Irish blood in him. Finding a convenient illustration in his faithful collie, he asked his friend to imagine the dog stretching itself, and yet stretching itself, until its head reached Glasgow, while its hindquarters remained in Oban. If he were then to tramp upon the dog's tail, it would bark at the Glasgow end. But he was careful to add that as it was not very convenient to stretch a dog so great a distance, the telegraph folk put up a piece of wire, which seemed to act just as well. While the Highlander's explanation may not make the details of electric telegraphs very clear to us, yet there is one point in the story which cannot be too well emphasized, and that is that there is a medium of communication between the two places, and this there always must be, even in the case of wireless telegraphy. Early in the world's history, man found it necessary to be able to signal to a distance, and so he adopted the method of lighting beacon fires upon the hilltops, and these signals could be passed on from one point to another. Of course, these men in ancient times had arranged with their distant friends that when a fire was seen upon the hilltop, it would mean a certain thing. When we moderns wish to communicate with our friends at a distance, we have to use prearranged signals in the same way. We find it convenient still to use visual signals for military and naval purposes, such as by the waving of flags. All such systems are limited necessarily to very short distances. When one sees a magnet turning first to one side and then to the other, according to the direction in which an electric current is sent through a coil, it is a very natural step from that to the first practical electric telegraph instrument. It is apparent that if one person had the coil and magnet in his house, and another had the battery at his home, while the wires still connected the battery to the coil, the second person could cause the magnet beside the first to move to one side or the other at will, and by an agreed code, intelligible signals could be transmitted. The needle telegraph is just this coil and magnet, and nothing more, except that it is put into a more convenient form. The magnet is fixed to a spindle, passed through its center, and then mounted in a vertical position at the back of an upright board. The coil is then placed around it, leaving the needle free to fall to the right or left. Then, so that the movements of the needle may be readily seen, an indicator or dummy needle is fixed on the other end of the spindle, which comes through to the front of the board. This indicator or needle moves, of course, along with the magnet at the back, and so the signals are clearly read. An arrangement for reversing the current at will in order to move the needle to one side or the other is added, and this may be operated by moving a handle from left to right, or by depressing one or other of two small levers or, quote, keys, unquote. It might be a matter of agreement to signal one movement of the needle for A, two for B, and so on, but the operator would very soon weary of this plan if he had many letters far on in the alphabet to count out. Imagine our written language being constructed thus: one vertical stroke for A, two for B, three for C, and so on. It's much more convenient to let two strokes leaning against each other with a third stroke crossing them stand for A. Three strokes placed thus for N, a vertical stroke, a slanted stroke, and a vertical stroke, and thus for Z, a horizontal stroke, a slanted stroke, and another horizontal stroke. And so in telegraphy it is agreed that if the needle is moved once to the left and then once to the right, this will signify A. It's quite remarkable that in order to construct the whole 26 letters of the alphabet by combinations of these two movements, we never require to move the needle more than 4 times for any letter. It evidently did not occur to the experimenters at the outset that this could be done, as they made the early instruments with 5 needles in order to get a greater variety of signal, their idea being to make the needles point out the letters on a dial. Referring to the accompanying alphabet, a figure in the text, it will be seen that the letters most often in use get the advantage of the simplest signals. Once to the left stands for E, once to the right for T, and so on. It's usual to print the left-hand strokes shorter than the right-hand ones, as shown but this is merely for convenience of space. Our own alphabet is a very simple construction. Give a boy 4 straight strips of cardboard, each representing a stroke, and he can with these construct more than half the alphabet, while a few semicircular pieces added will enable him to complete the whole 26 letters. While Cook and Wheatstone were the first, 1837, to set up a needle telegraph in this country, we cannot claim the invention for them, as Professor Ampère of Paris had suggested 15 years earlier that a magnet and coil placed at any distant point of a circuit would serve for the transmission of signals. And other experimenters in Germany had actually carried this out with success. Simple as this method is, there was a yet simpler plan adopted in New York about the same time as the former was set up in London. Knowing that an electromagnet would attract and let go at will, a piece of iron was suspended by a spring so that it stood close over the poles of the electromagnet. Whenever a current was sent along the wire to the electromagnet, it would attract the iron and hold onto it as long as the current was left on. But as soon as the circuit was broken, the magnet lost its power so that the iron was pulled away by the suspending spring. The movable piece of iron was mounted on one end of a small lever, the other end of which worked between 2 stops, so that each time the iron armature was attracted downwards, it caused the other end of this lever to click against the upper stop, and by this means signals or intelligible raps were made. If the lever clicked against the upper stop and then immediately fell back onto the lower stop, that indicated the letter E. But if after striking the upper stop, it remained a little before falling back on the other stop, then the letter T was signaled. If the lever gave 3 quick successive clicks, the letter S was to be understood, and so on. This method saves the trouble of reversing the current, which was necessary in the needle telegraph. All that is required in this American invention is to make and break the current's path. While this system of telegraphy had been suggested by a great American scientist, Henry, as early as 1831, it was not until 1837 that another American, Morse, brought the instrument into practical use. Working by clicks, it is called the, quote, Morse Sounder, unquote. Morse also arranged that the instrument should record the signals received by marking them on a strip of paper, and this has been termed a, quote, Morse inker, unquote. If one end of the armature lever is fitted with a small wheel, which when at rest dips into a small inkwell, and if, instead of coming in contact with a stop when raised, the wheel touches a paper ribbon, which is kept in motion by clockwork, then a mark will be made along the center of the paper as long as the wheel is held up by the magnet at the other end of the lever. It is therefore an easy matter to make long or short strokes at will by keeping the current on for different lengths of time. That is all this instrument can do, make short and long strokes, usually called dots and dashes, and the alphabet is made up by different combinations of these. The letters E and T, being used oftener than any other letters, get the advantage of a single short stroke for E and a single long stroke for T, as will be seen from the accompanying alphabet in the text. It will be noticed on comparing the Morse and the needle alphabets that they are really identical, a short stroke or dot being equivalent to the needle falling to the left, and a long stroke or dash to a needle movement to the right hand. With constant practice, this alphabet becomes as natural to the operator as our everyday ABC, and I have heard of 2 telegraph operators carrying on a silent conversation with each other by a slight movement of the left and right eyes. Underneath the Morse alphabet in the text will be found a short sentence of 2 words, which may be easily deciphered. A bald statement that an electric current must always have a complete circuit does not appeal very forcibly to many minds. I have seen people quite at sea in trying to arrange a simple electric circuit, such as connecting up a bell, push, and battery. There need not be the very slightest confusion if one clearly keeps in mind what is taking place when a battery sends a current of electricity along a wire. All that the battery does is to cause an electric current to pass from its carbon plate to its companion zinc. We fix a short wire across from the one plate to the other, and an electric current passes along the wire on its way from the carbon to the zinc. We may make the wire a mile long, or as long as we please, and the current must pass by this route on its way from the one plate to the other. If we carry the wire to Land's End and back, then before the current can get from the carbon to its close neighbor, the zinc plate, it is forced to travel via Land's End. If the wire circuit is broken at any place, the current immediately ceases, as it has no path left from the carbon to the zinc. If the wires are touched together again, the current once more passes. The ordinary electric bell push is merely a means of making and breaking the circuit. If the wire of our imaginary Land's End circuit be cut at that distant place, and the two free ends be joined to the two ends of the coil in a needle telegraph instrument, then the current in going from the carbon to the zinc in the battery has to pass through this distant telegraph instrument, as its coil has become part of the circuit. The necessity for a complete circuit is therefore quite apparent. While fitting up a telegraph installation on a railway in 1838, Steinheil of Munich noticed that his return wire was broken, and that the two ends were put into the earth. The current passed through just as though the wires were joined together. It was soon found that it did not matter how far distant these earth connections were, so that if a telegraph is to be fitted up between London and John O'Groats, a wire is led from the carbon in the battery at London all the way to that northern limit of the Scottish mainland, and there connected to one end of the telegraph coil. Instead of now bringing a return wire from the other end of the coil right back to the zinc of the London battery, a short wire is simply connected to the earth at the Scottish end, while at the London end another short wire is led from the earth to the zinc in the battery there. At the London end, it would be quite sufficient to fasten the short wire from the zinc to any water pipe in the building, and therefore get into contact with the earth. But not finding a similar convenience at the northern house, it would be found necessary to attach the wire to a copper plate, and then bury it in the moist subsoil. In Figure 6, an earth circuit is shown in which both ends are attached to buried plates. It was originally supposed that the current of electricity passed through the earth from the one plate to the other, but it seemed afterwards more reasonable to picture the current as being dissipated in the earth at the one end and fed on at the other end. An analogy portrays the earth as a great ocean, the wire like a pipe with its two free ends dipping into the ocean at far separated points, and the battery is a pump propelling the current along. Whatever mental picture we form, we must remember that the electric current is not a material fluid. There is no difficulty in sending a current over this single wire with its earth circuit, but one is not surprised to learn that when any great natural disturbance takes place in this ether ocean into which the wires are dipping, the current in these earth-connected wires is very appreciably affected, our whole telegraph system being sometimes quite upset during a magnetic storm. End of Chapter 6.
Chapter 7 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Romance of Modern Electricity by Charles R. Gibson. Chapter 7. How We Now Send Telegrams. Beginning of public telegraphs. A telegram outruns a murderer. Impetus to telegraphs. Government takes control. A country postmaster baffled. Speech wired in half the time of delivery. How high speeds are attained. How a falling current hands the signals to a vigorous current. Several messages pass simultaneously on one wire. Some clever inventions. Ordinary writing by telegraph. Typewriting telegraphs. Enormous telegraph business. Telegraph versus telephone. When His Majesty the King was born, in 1841, the good news was not heralded across the country by the telegraph, for the very good reason that not a single telegraph line connected any two towns together, the invention having only been applied to a few short private lines along the railways. In the United States, things were in very much the same position, the first commercial line of telegraph not being opened until 1844, when Washington was connected with Baltimore. One would have expected this great invention to be received by the people with open arms, but in this country the inventors could not get anyone to take an interest in the matter excepting railway companies, which were at the time few in number, so that the first 5 years' working entailed a serious loss to the investors. How long things might have continued in this way but for a chance incident it is difficult to say. And indeed, one would not have been surprised to learn of the investors determining to abandon the scheme and to lose no more money. It so happened that a Quaker, having committed a murder near Slough, fled to the Great Western Railway and took train to London. But the news of the dreadful deed reached the station at Slough soon after his train had left. One can imagine the disappointed pursuers possibly thinking, quote, "A miss is as good as a mile," end quote, for no living being could hope to overtake the train. But someone suggested getting the railway officials to send word over their telegraph line to London. A full description of the Quaker and particulars of what had happened were spelt out by the needle telegraph, so that the murderer, while no doubt congratulating himself that he had outrun any chance of arrest, was startled to find that news of his crime had reached London before him, as he was quote, "shadowed," end quote, on his arrival, and quietly arrested. One can imagine the news of this wonderful capture spreading through London and from town to town, till the country began to praise the telegraph as a right useful messenger. Investors, who had previously looked upon the electric telegraph as too risky a business, would now be most willing to give financial support. The Electric Telegraph Company was soon formed, and within 3 years about 1,500 miles of wire were erected, and before our king was 8 years of age, London, Birmingham, and Manchester were in direct communication by telegraph. It was not long before other private companies were formed. A telegram in those days meant important news. Even the wealthy would not have thought of wiring such messages as, quote, "We'll come to see you tomorrow afternoon. Wire if convenient," end quote. For such a telegram would have cost 4 or 5 shillings, even for a short distance, while the minimum charge between London and Edinburgh or Glasgow was 12 shillings. After about 10 years' working, one of the telegraph companies tried to adopt a universal rate of 1 shilling, but the opposition of the other companies was too strong. 5 years later, all the companies agreed to a big reduction in rates, with the idea of increasing business, and this proved a great success. It is very well that the government took over the telegraph business in 1870, for it was only natural that the private companies would not extend their telegraph lines into districts where they could not hope for a profitable return. The government could afford to take a less mercenary view, and small towns and villages soon had their post offices connected by telegraph with the nearest large town, till now a perfect network of wires extends across the country in all directions. It is impossible to overestimate the value of the electric telegraph to the world, and yet it would not be surprising to find some people willing to denounce this invention as the destroyer of the once peacefully quiet life of the, quote, "good old times," end quote. There is no doubt that the electric telegraph and the steam engine are the two chief factors in producing the hurry-scurry of the present day, but surely it is quite unnecessary to set forth the very great advantages which these inventions have brought into our everyday life by putting us in touch with all the ends of the earth. The speed with which intelligence could be conveyed to a distance by the electric telegraph, as compared with all previous methods, was so very great that the actual time required in manipulating the instrument was at first counted of small moment. But with the consequent hastening of business methods and the extended use of the telegraph system, A great deal of attention was soon given to means of increasing the speed at which messages could be dispatched. In country districts there may still be found some of the ABC dials, by which a word is slowly spelt out by causing an indicator to move round a dial and point out the letters of the alphabet separately. I remember many years ago going into a little country post office to dispatch a telegram, and being informed by the elderly "postmaster" that he couldn't get his machine to work. He explained that it had just been fitted up, and that he found they had given him no bottles to work it with, such as he had seen at the neighboring village. I suggested that possibly his "machine" didn't require any bottles, which proved to be the case, as he had one of those ABC dials in which no battery is required, the current being obtained by driving a little magneto machine in exactly the same fashion as one rings up on a telephone. Of course, the advantage of these instruments for country districts was that the operator required to learn no special code or alphabet, but these would only be tolerated now where speed is of little consequence. Even the needle telegraph, which is purely an English instrument, is much too slow and is only used now for small districts and in signal cabins on the railway. The Morse "sounder" described in the preceding chapter is almost universally used both in this country and in the United States for ordinary business. As it is necessary for the operator to spell out each word and space the dots and dashes correctly, it will be apparent that even in the hands of a skilled expert the time taken in sending a message must be very much longer than the time required to speak the words. One might easily speak 180 words in a minute, but an operator could not signal more than 35 words comfortably in the same time, so that a 2-hour speech delivered in Parliament, when telegraphed, would occupy a line from London to another important centre for a whole night, which would be a serious matter for the economical working of the post office. Fortunately, this is not necessary, and although it may seem incredible, it is a fact that a 2-hour speech may be passed over a single line in less than half the time taken to speak it. While the speech is in progress, the reporters may hand their copy to operators who prepare a paper ribbon in a punching machine, making holes to represent the Morse signals. With a full staff of reporters and operators, the whole copy of the speech may be thus ready on the punched ribbon almost as soon as the delivery of the speech is finished, and it is only necessary then to run this paper by clockwork through a special transmitter, thus causing the makes and breaks of contact, by means of the perforated holes, at a speed far greater than can possibly be done by the quickest expert's hand. The Wheatstone automatic sender, which is in general use, can easily transmit at a speed of from 250 to 400 words per minute, the former figure being counted a fair working speed over a distance. It is in connection with the automatic transmitter that the Morse inker is chiefly used to receive the signals, but the latter may, of course, be worked by an ordinary hand key as well. If an automatic transmitter were merely sending signals to a "Morse Sounder," it would be quite impossible to read the clicks by ear. If they were coming in at a speed of about 300 words per minute, then there would be as many as 4,500 clicks made against the upper stop in 1 minute, which is equivalent to 70 signals in each second of time. Therefore, without the Morse inker, the automatic transmitter would be of no service. The most important use of the automatic transmitters is for press news, but they are also used for ordinary messages on busy lines. At the larger telegraph offices, all the instruments are supplied with current from a storage battery, the number of cells for any one line depending upon its resistance. The longer the wire, the greater the resistance, and therefore the more pressure required to send the current through. In order to decrease the resistance on long wires, they are made of better conducting properties. When an electric current has traveled a long distance, its strength is considerably reduced owing to the resistance of the wire, so that an electric impulse, on reaching a far distant town, may not have sufficient energy left to cause the electromagnet to attract the comparatively heavy armature required to make a distinct sound, or to cause a recording instrument to impress the signals clearly on paper. This apparent difficulty is very easily overcome, for as long as there is a very small current, this will be sufficient to cause a small electromagnet to attract a very light lever, and the movement of this lever can switch on a local battery to the telegraph instrument. This small electromagnet and lever arrangement is called a relay, or repeater, and when the operator depresses his key, or when he makes a series of up and down movements, the electromagnet of the distant relay causes its lever to make a similar number of up and down movements, so that this lever exactly imitates the sending key and operates the telegraph instrument to which it is attached. On going into the telegraph room of a large post office, the stranger merely hears a meaningless rattle of clicks, but to the experienced telegraphist, it is just as though he were in a crowded room and heard a number of conversations being carried on by different parties. The operators sit in rows at narrow tables or benches, to which their telegraph instruments are fixed. The wires pass along these tables, one wire leading from the battery room to the operator's contact key, and the other wire back along the table to a board whereon are fastened all the ends of the outside telegraph lines. One does not find a great network of wires over a large telegraph office, because the wires are led through the city underground, and then they branch off in all directions, carried on the familiar telegraph poles. These overhead wires have often been a great source of trouble during a severe storm of wind or snow, their downfall causing serious dislocation of commercial business, so that the post office has been forced to make some of the connections between the more important cities by insulated wires buried in pipes in the earth. Even with overhead connections, each wire means a considerable expense, and so telegraphists found means of sending more than one message at a time over a wire. It seems to the stranger quite ridiculous to attach several telegraph instruments to each end of a single wire. One would expect an utter confusion of signals, but it is not so. Every line of importance in this country is, quote, duplexed, end quote, to carry two messages at one time, there being, of course, two operators at each end. One of these operators sends messages, while his local partner is receiving messages from the distance, and yet there is no confusion. It would be difficult to give a clear statement of how this is done without going into technical details, so I shall merely remark in passing that one may picture the receiving instrument as being electrically shielded from the outgoing current leaving the same station, and only affected by the incoming current, so that a transmitting operator at each end is sending messages out to a receiving operator at the opposite end of the wire. At large centers, 8 operators use one wire at the same time, there being 4 operators at each end. 2 operators are sending messages out, and the other 2 are receiving messages, and each receiver picks up its own message in this manner. A current is kept constantly flowing on the wire. Neither receiver is affected by this current, but a change in the strength of the current operates the one telegraph, while a change in direction of the current moves the second receiver. Inventions have been made whereby a larger number of messages may be sent over a single wire simultaneously, but these are not in everyday use. In one system, it is arranged to have each operator the use of the wire in turn. his turn recurring as quickly as he can possibly make use of it. This system requires a rapidly revolving connection at each end of the wire, both mechanisms keeping perfect time, and the mechanical difficulties of keeping these two motors in absolute harmony with each other has proved too much for ordinary practice. Another inventor sends as many as a dozen messages at one time over a single wire, using telephone receivers, with each hum a different sound, each telephone replying to its own signals only. The sounds, of course, represent the clicks of the Morse alphabet. Among other recent inventions is one in which a perforated tape is prepared to transmit currents to a distant receiver which contains a tiny mirror, throwing a spot of light onto a photographic paper. The movements of the mirror are so controlled by the current that the pencil of light traces out the different letters of the alphabet upon the paper. It reminds one of a boy reflecting the sun's rays against a wall by means of a small mirror. He can make the spot of light dance about at will, and if the irresponsive wall would only retain the impression of the spot of light, the boy could write upon the wall with his pencil of light. In the telegraph instrument, one particular set of perforations passing through the transmitter causes the tiny mirror in the receiver at the distant end to move so that the letter A is traced upon the photographic paper. Another set of perforations produces B, and so on. The photographic paper, after receiving these impressions, is chemically developed and fixed by the receiving instrument. This instrument has the advantage of a very high speed in working, as many as 40,000 words having been telegraphed over a considerable distance in 1 hour, which means that the whole of the text of this book could be telegraphed in less time than one could read a quarter of its contents. Another advantage is that the receiving instrument delivers the message to the operator in ordinary writing. For the reception of press news, this advantage is rather lost, as it is necessary for the post office in any case to write out a number of copies by means of a manifold book, sending one copy to each of the local newspaper offices. An expert will read the regular Morse signals about as easily as the ordinary ABC, so that the longhand written message is of no great advantage to him. There seems to be a large field open for typewriting telegraphs. These have been used on the continent for a long time, but one disadvantage has been that the message was written on a tape or ribbon of paper. There is great activity in this line of invention at present. One inventor uses a typewriter to prepare a perforated tape, which is run through the transmitter, operating the distant receiver, which produces a similar perforated tape, which in turn is run through a special typewriter, producing the message in letter form. This may seem a somewhat roundabout method, but the object is to gain a high rate of speed in transmission over the line. Other inventors are at work with type wheels in the receiving instruments to be controlled by a distant transmitter having keys similar to a typewriting machine. The message to be in page form, ready for delivery. This is really equivalent to having the keys of a typewriter at one end of the line wire, while the types are at the distant end. There seems little doubt we shall one day receive our telegrams in typewritten form, just as produced by the telegraph instrument. There is an invention of long standing by which one may write in ordinary hand, using a pen connected to some electrical mechanism, and a pen in the distant receiver will exactly imitate every movement of the pen in the transmitter, so that one may write a letter or sketch a picture on the transmitter, and a reproduction will simultaneously appear at the distant receiver. This apparatus is most ingenious, and would, no doubt, have come into general use for private lines, but for the advent of the telephone. The telegraph business has grown to an enormous extent. In Great Britain alone, There were 93 millions of telegrams passed over the wires in the year 1903, while the United States of America followed closely with 91 millions. France and Germany each handling about half as many, while Russia and Japan dispatched 19 and 17 millions respectively. But for the growth of the telephone system, there is no doubt these totals would have been much greater by this time. However, taking the grand total of the 6 countries above mentioned, one finds that these countries among them handle about 1 million telegrams every day of the year, omitting Sundays. The total of telegrams handled by the British Post Office in 1904 was about 3 million less than in the previous year, and no doubt one of the main causes of this decline has been the rapid increase of telephonic communication. While Great Britain leads in telegraphic messages, it comes far behind with its telephone total. In the United States, over 5,000 millions of telephone messages have been exchanged in 1 year, so that for every telegram dispatched in America, 50 telephone conversations took place. There is not the least probability of the telegraph being ultimately eclipsed by the telephone for long-distance work, but great changes will doubtless take place within the next generation, and it may be that the telegraph will become the usual means of transmitting ordinary business correspondence at a very low rate. End of Chapter 7.
Chapter 8 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Electricity by Charles R. Gibson. Chapter 8. Telegraphing Across the Sea. Early attempts to lay submarine cables. A bold proposal. The first Atlantic cable. A long chapter of accidents. Success and failure. The Great Eastern's task. A search for a lost cable. How the messages are signaled. A wondrously sensitive instrument. How cables became faulty. How faults are located. Early prices for cable messages. A cable behaves quite differently from a bare wire. A young man reads a prophecy in the fulfillment of which he is afterwards destined to take a prominent part. It is a comparatively easy thing to connect 2 places on land together by means of a wire stretched between poles right across the country, but to attempt to connect 2 places with a vast ocean between is a much more difficult task. In the early days of land telegraphy, many experimenters tried to lay an insulated wire underwater, but with varying and short-lived success. After one almost complete failure in attempting to connect Dover with Calais, which exploit was generally accounted a mad freak, it required a sanguine man to raise a sum of £15,000 to make a second trial. It is to the credit of Mr. T.R. Crampton, an eminent railway engineer, that he not only raised the sum in 1850, but that he subscribed half of the required amount out of his private purse. It was not without difficulty that even this comparatively short cable was laid, but the success that attended it gave promise of greater achievements. Further advance was not to be all plain sailing, for 3 different attempts to connect England and Ireland only ended in sinking expensive cables that were quite unable to withstand the strong tidal currents, etc. A 4th attempt with a much heavier cable fortunately proved successful. It was soon boldly proposed that an attempt should be made to span the great Atlantic Ocean, and thus connect Europe with America. This was indeed a bold suggestion, for the laying of all previous cables was mere child's play when compared with the spanning of a great open ocean, measuring at places nearly 3 miles in depth. It is somewhat surprising that there was not much difficulty in raising a capital of £350,000 towards the laying of an Atlantic cable, which must needs have been pretty much of an experiment. It is difficult even to conceive the magnitude of the task of manufacturing a cable over 2,500 miles in length, but some idea of the stupendous work may be obtained by a mere statement of the fact that this cable, which was made of several strands of copper wire for the conductor, with a substantial insulation of gutta percha and an outer protection of iron wires making, as it were, an iron rope with an insulated core, required a total length of wire more than sufficient to stretch from the earth to the moon. However, The manufacture and also the stowing away of the cable into the holds of one British and one American man-of-war were easy tasks as compared with the difficulties in laying the cable safely on the bed of the great ocean. Having left one end of the cable on the Irish coast, the American warship steamed slowly away. But before a paltry 5 miles of the cable had been paid overboard, the cable caught in some of the paying out apparatus and parted. The lost end was with difficulty found by tracing the cable from the shore end. After splicing this to the rest of the cable, all went well for a few days, but once more the cable snapped, leaving some 380 miles at the bottom of the ocean, the broken end going to a depth of 2,000 fathoms. The ships had to return home and abandon the lost cable, but ultimately recovered 50 miles of the shore end. In the following year, 1858, the great ship steamed off once more with some 3,000 miles of precious cable, and with improved machinery for paying out. Previous to starting on this second voyage, the steamers had made extensive experiments in laying some defective cable in the Bay of Biscay in order to test the new machinery and give practice to those responsible for its control. On this occasion, it was decided that both steamers should begin in the middle of the ocean, and after splicing the two cables together, pay out in the directions of the two shores. This plan was proposed at the very outset by the engineer-in-chief, but was objected to by the electricians, who preferred that one steamer should lay half of the cable from the Irish shore to mid-ocean, where the other ship was to join up its cable and lay the second half to the American shore. However, it was decided to try the mid-ocean start this time, but before reaching mid-ocean, the British war vessel was almost lost in a storm, owing to the great dead weight she carried. Having met and spliced the cables, the two ships had not gone many miles paying out the cable when it broke, and another start had to be made. During the laying of the cable, electrical communication was kept up between the ships through the whole length of the cable, and after some 40 miles had been paid out in the second attempt, the electrician, late Lord Kelvin, reported to those on deck that another break had occurred, apparently at some distance from the steamer. Another meeting in mid-ocean, another splicing of the remaining cables, and the two vessels again made off for the distant shores. But after each steamer had laid over 100 miles of cable, yet another break occurred. At the last mid-ocean meeting it had been arranged that if a further break occurred before 100 miles of cable had been paid out from the start, the ships should once more meet. But if the cables snapped after they had passed 100 miles, they should each make for Queenston. Those on board the British man-o'-war decided to return to mid-ocean, as the break occurred only a few miles beyond the limit. But after hanging about the meeting place for some days, they found that the other vessel had evidently kept to the exact instructions, so that there was nothing for it but to return home too. This was very disheartening, but it is most fortunate that, though the chairman of the cable company urged the abandonment of the whole scheme and the realizing of what cable was left, it was ultimately decided that another attempt should yet be made, and the vessels set off for the agreed dot upon their respective charts. On this occasion, after many narrow escapes and much anxiety, the two ends of the cable were safely brought to their respective shores from the splice in mid-ocean, amidst much rejoicing on both sides of the Atlantic in the August of 1858. After congratulatory messages had been dispatched and reciprocated, the first piece of public news sent over the cable was the information from New York of a collision between two of the Cunard mail steamers, compelling the outgoing vessel to put back to port. The message informed the friends in Europe that no lives were lost, and so spared them the anxiety that would otherwise have been caused by the non-arrival of the great steamer at her appointed time. Among the early messages was one from the British government to the generals of two British regiments stationed in Canada. Orders had been sent by mail that the regiments were to return at once to England and proceed to the east to help in suppressing the Indian mutiny. But meantime, the mutiny was quelled, so that there was no need of the assistance of these troops. The next mail would have been too late to cancel the orders, but by means of the new cable instructions were immediately sent, thus saving a sum of some 50 or 60,000 pounds. The troubles of the cable company were not all over yet, for very soon the long submarine conductor showed signs of giving out. The messages became less and less distinct until they grew so faint that the signals were confused and ultimately died away altogether. During its short life, the cable had carried between 700 and 800 messages, but if a cable was only to last a short time, it would not pay to lay one. After much consultation and experimenting, it was determined that the cause of the failure was the use of too great intensity of current. Instead of merely using a battery, as had been done in testing on board ship, the electricians had greatly intensified the current by means of large induction coils. It was with difficulty that after a lapse of some years new capital was raised to make another attempt in 1865. Past experience helped in the manufacture of a better cable, both as regards to strength and conductivity. It was on this occasion that the Great Eastern, which had proved a white elephant for trading purposes, having lain idle for the greater part of 10 years, was employed to carry the whole of the new cable and to commence laying it from Britain to America. After several delays, owing to faulty parts in the cable, a break occurred which proved a serious trouble. Several attempts were made to recover the broken end, which was discovered and hooked 3 different times, but it was found impossible to get it raised, so that the Great Eastern had to return home with her task unaccomplished. Nothing daunted, the company raised new funds, not only to lay another cable, but to attempt the completion of the lost one also. Both of these attempts proved successful in the following year. It would seem almost ridiculous to attempt to find the end of a lost cable in the middle of a vast ocean, but as particular note of the longitude and latitude of the place had been made at the time of the loss, the searchers were able to get somewhere near the lost treasure. With patience, the cable was at last found, but there were many sore disappointments before it was brought to the very surface, and even then it slipped away like a living sea monster more than once, until the task began to seem quite hopeless. On one occasion, there was much rejoicing when the end of the precious cable was apparently brought on deck, but one can imagine the feelings of the patient toilers when it was discovered that they had merely hooked a few odd miles of faulty cable which had been used in some experiments. After many failures, and just when about to give up in despair, the cable was at last brought on board from some shallower depth, and the sense of relief must have been great, as the electrical test proved it to be still in a working condition. At the shore end, those in charge must have almost given up all hope. But when in the quietness of a Sunday morning the watcher at the receiving instrument saw apparent signs of life, how eagerly would he decipher the signals and carefully note the message, which read, "Ship to shore. I have much pleasure in speaking to you through the 1865 cable, just going to splice." Those who had secured the lost cable would feel justly proud that they succeeded in completing the whole length. It was now clear that ocean telegraphy had come to stay. Many other cables were laid from place to place, and the cable companies of today do not hesitate to sink £500,000 sterling in a single cable across the Atlantic, while a whole fleet of cable repairing vessels is constantly stationed in various parts of the world. The telegraph apparatus, and even the delicate relay as used on land wires, are much too heavy to be used on long submarine cables, so that it was found necessary to have a much more sensitive receiver, although for short cables, such as across the Irish Channel, etc., ordinary Morse anchors are worked by the post office. It was by the inventive brain of Professor William Thomson, late Lord Kelvin, that a suitable instrument was devised. The principle upon which this works is very simple, and is in point of fact the same as already described in the needle telegraph. It will be remembered that the current passing in the coil of wire caused a magnetic needle to swing round. In this more delicate apparatus a very tiny magnet is suspended by a silk fibre inside a small coil of very fine wire, but as a small movement of this little magnet could not be easily seen, there is attached to it a tiny mirror, which along with the magnet weighs only about a single grain. A lamp throws a fine ray of light through a slot in a screen, and this, falling upon the mirror, may be reflected upon the wall or upon a graduated scale. By this ingenious method, a very small turning of the tiny magnet gives a large motion to the spot of light, as every boy who has annoyed his neighbors with a small sun reflector will well understand. At the present time there is a story going the round of daily papers and magazines to the effect that the use of a small mirror was suggested to Lord Kelvin by his eyeglass falling and dangling before him. But I think we may safely label the story as pure fiction, without referring to the matter of his lordship, for of all men Lord Kelvin would be well versed in every previous electrical device, and there is on record an early telegraph by 2 German experimenters in which they used a mirror to indicate the turning of the magnet, though it was a very clumsy affair. This fact does not detract from Lord Kelvin's invention, the beauty of which is its great sensitiveness, and the suggestion to use the reflective ray of light to point out the movement of the tiny magnet instead of attaching a pointer or indicator to the magnet and thus increasing its weight. This instrument is known as the Mirror Galvanometer, and it is used for making delicate tests. The same great genius devised a means by which the movements of the little magnet might record the signals. The construction of this instrument, which is termed a Siphon Recorder, is somewhat different from the Mirror Galvanometer just described, but the principle is the very same. A very fine glass tube has one end dipping into a small well of ink, and the other end close to a paper ribbon, which passes along by clockwork. This little tube acts as a siphon to carry the ink from the well to the paper, and it is operated by the little magnet so that it is drawn to the right or the left in sympathy with the movements of the magnet. In this way, a record of the signals is taken, as shown in Figure 7, in which the right and left movements are easily discerned on either side of the dotted line. The alphabet is the same as in the simple needle telegraph, so that the letter A, which is indicated by the needle falling first to the left and then to the right, will appear on the cable paper as shown in the accompanying diagram. It is interesting to note that in order to get the ink to flow freely through so fine a tube, the inventor found it was necessary to electrify the ink. The idea, no doubt, was suggested by a discovery that was made in 1780, that water issuing from a nozzle in drops would flow in a stream if electrified. At a later date, it was found that if the siphon was given a vibratory motion, the same result was obtained. Returning to the subject of the long submarine cables connecting distant lands, it will be quite evident that after a cable is safely laid at the bottom of the great deep, it may not be in a very stable condition. If a cable were to be laid across the country from a balloon, there would probably be many hilly places where the cable would not touch the ground, but would stretch from one hillside across a valley to another hill. And so it happens in a similar fashion that there are many rough places at the bottom of the ocean where the cable stretches across a valley, and at such points it may easily become strained and ultimately broken by a rubbing friction caused by ocean currents, etc. Then again, the cable may be slowly destroyed by chemical action in certain waters, or serious injury may be caused by submarine earthquakes. Or, as has sometimes happened, a cable has suffered from attacks made upon it by some sea monster. On several occasions, teeth of such monsters have been found embedded in the cable coverings at places where faults occurred, and at least twice has a great whale been found entangled with a cable. It would be a very serious matter when a fault occurs and signals become weak or altogether cease if the repairing squad had to make an examination of the whole cable in order to locate the fault. Such a task would indeed be 1,000 times worse than looking for a needle in a haystack. But fortunately for the success and the economy of cable companies, it is possible to find out in a very simple way exactly whereabouts the fault has occurred. Every wire or cable offers a certain amount of resistance to the passage of an electric current according to the size and quality of the wire, and a particular note is kept of the exact amount of resistance a mile length of each cable offers. If a cable breaks at any point, then the current gets to earth at that place, and by passing a current into the cable, it can be seen by a galvanometer how much resistance is being offered to the current. For the smaller the resistance, the more current will flow. Having found the total resistance to the current, it is easy to calculate the length of the cable that offers such resistance, and if it be found to be equal to the resistance of 110.5 miles of cable, then it is known that the break has occurred at that distance from the short end, while the chart of the route will give the latitude and longitude of the particular place where the broken end must be lying. In the Atlantic Ocean alone, there are sunk some 40,000 miles of cables, giving constant employment to a very large staff of workers, clerks, etc. Commencing with a charge of £20 for 20 words, the price soon came down 50%, and then to 30 shillings for 10 words, at which figure it stood for a long time. In 1872, the price stood at 4 shillings per word, but thanks to increased business and competition, we can now afford to cable very ordinary business or private messages at a rate of 1 shilling per word, and if the rate should drop to 6p, the public on both sides of the Atlantic will no doubt take a correspondingly increased advantage. One great difficulty in telegraphing across the seas is that an insulated cable behaves quite differently from an ordinary bare telegraph wire. The cable becomes charged something like a Leyden jar, and thus retards the flow of the current, so that special condensers require to be used to assist the current. The automatic transmitters described in the preceding chapter are also used on cables, but not so much for speed as to obtain a regularity of signals. Lord Kelvin's connection with the pioneer cables is well known, but I have been very much interested to learn from Dr. David Murray that he remembers being present at a meeting of the British Association held at Glasgow in 1840, at which a model of Ponton's galvanic telegraph was exhibited, the description of which is enclosed with the sentence, "The further improvement of this instrument and a more familiar acquaintance with its use may ultimately lead to connections being made between the most distant countries in the world for the transmission of intelligence, and prosperity may perhaps witness the receipt of such news from India by means of galvanic telegraph in as many minutes as there are a week now occupied in the conveyance of a dispatch." It is remarkable that this apparently long look ahead was fulfilled for that generation, and that a young man, William Thomson of Glasgow, who was present at that meeting, became the chief actor in this great historical event. While the name of Sir William Thomson, afterwards Lord Kelvin, stands out very prominently in connection with the first Atlantic cables, it should be noted also that a great deal of success in laying the cables was due to the ingenuity and skill of the late Sir Charles Tilston Bright, who designed and supervised the working of the paying out machinery. As engineer-in-chief, Bright had many difficulties to contend with, and although only 26 years of age at that time, he overcame all these troubles, which many of the leading men of that day said were insurmountable. End of Chapter 8. Read by Lindsay Strausser. Jacksonville, June 2022.
Chapter 9 of the Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Martin Hill. The Romance of Modern Electricity by Charles R. Gibson. Chapter 9. Some Early Attempts at Telegraphy. An ingenious surgeon in Scotland invents an electric telegraph 150 years ago. Other inventors. The great difficulty these early experimenters had to contend with. The beginnings of the practical telegraph. 30 connecting wires reduced to one single wire. A very easily satisfied British government. One would not expect to find any attempt at telegraphy in the days when man's only knowledge of electricity was its wild and sudden discharge from an electrical machine. And yet there exist on record several very interesting attempts in those days prior to Volta's taming of electricity into a peacefully tractable current, as we have it from batteries. It is evident that some attempts to transmit intelligence by electricity were made as far back as the middle of the 16th century, although the records of these are somewhat vague and appear to have been carried out by some monks in a German monastery. In the Scots Magazine of February 1st, 1753, there appeared a letter describing a practical electric telegraph worked by a primitive electrical machine. The letter was merely signed C.M. and was written from Renfrew, a small town on the River Clyde, a few miles below Glasgow. The one property of electricity with which this ingenious writer would be most familiar was doubtless the attraction between an electrified body and any light object placed near it, and so it occurred to him that if he could charge a long connecting wire between two places, then the distant end would attract a small piece of paper placed close to it. Having determined that this could be done, he set up 26 separate wires, connecting his dwelling to a distant cottage in the village. The wires were supported on insulators at short distances apart, being fixed at each of the two distant ends in a bar of solid glass, leaving about 6 inches of wire extending beyond the glass fixture. These 6-inch ends were stiffened so that if depressed, they would spring back to their horizontal position. These free ends were then placed immediately above the glass cylinder of an electrical machine, so that while the machine was excited by rotating it, any of these 26 ends could be pressed down to touch the cylinder, and thus the whole length of this particular wire would receive a charge of electricity. At a point close to where each wire entered the solid glass fixture, the inventor suspended a short piece of wire with a metal ball at its extremity, there being, therefore, 26 separate balls. Immediately under each ball he placed a small piece of paper bearing one letter of the alphabet upon it. This arrangement was, of course, carried out at both ends of the line wire. To signal the letter A, the operator, having set the electrical machine in motion, would take a piece of solid glass in his hand, and, depressing the end of the first wire till it touched the cylinder, he would charge the whole of that wire, so that the suspended metal ball at each end would attract its particular paper marked A. The person at the receiving end would take note of A, while the operator would see by the attraction of A at his own end that the wire had been sufficiently charged. In the same way, all the 26 letters of the alphabet could be signalled in any desired order, thus enabling intelligible messages to be sent. The inventor says that the letters were contrived to fall back into their proper places, so he may possibly have had a small glass division for each letter to rise and fall within. The inventor also suggested, among other arrangements, that each of the little metal balls might by attraction be made to strike against a little gong, there being 26 gongs of different sounds, and the person using the apparatus would, as the inventor said, soon understand the language of the bells. In this suggestion we have the first idea of a sounder telegraph, and it is by sound signals that most telegraph messages are now received. The great difficulty in working any such apparatus as that just described would be to prevent the high-tension charge from making a dash to Earth through every possible means of escape, and in this connection it will be of interest to note a few sentences from the inventor's letter. He writes, "Some may perhaps think that although the electric fire has not been observed to diminish sensibly in its progress through any length of wire that has been tried hitherto, yet as that has never exceeded 30 or 40 yards, it may be readily supposed that in a far greater length it would be remarkably diminished, and probably would be drained off in a few miles by the surrounding air. To prevent this objection, and save further argument, lay over the wires from one end to the other with a thin coating of jeweller's cement. This may be done for a trifle additional expense, and as it is an electric per se, will effectually secure any part of the fire from mixing with the atmosphere." Here we have, at this early date, the idea of an insulated wire, as used for almost all electrical purposes at the present time. It is interesting to note that the mental picture which this ingenious man formed of electricity was that of a fire, which thought was very natural, owing to the appearance of a spark at any point where the electricity suddenly escaped from one body to another. The late Sir David Brewster made particular search to discover the history of this anonymous letter-writer, C.M., and his efforts met with a certain amount of success. He first of all found out that a very clever man had lived in Paisley in 1791, that he came from Renfrew, which is only a few miles distant, and that it was reported of this genius that he could light a house with coal-reek smoke, and make lightning speak and write. At a later date, Sir David Brewster found that this man's name was Charles Morrison, who was a native of Greenock, but practised for some time as a surgeon in Renfrew, and ultimately became connected with the tobacco trade in Glasgow. Morrison was counted a wizard, and his neighbours believed him to be in concert with the devil, because of the apparently supernatural power he had of sending messages to a distant cottage. He ultimately went out to Virginia, US, where he died. Another early form of telegraph suggested was that the sender and the receiver should each have a good clock, with the letters of the alphabet painted round the dial, and the two clocks keeping accurate time, the second hands would point to the same letter on each dial at the same moment. By a connecting wire between the distant places, a Leyden jar was made to spark at the moment the hand was opposite the letter that the sender wished to telegraph, the receiver also noting the letter indicated on his clock at the moment when the spark occurred. The first idea of this inventor had been the very primitive method of striking, with some object in his hand, upon the bottom of a copper stew pan at the moment his clock was at the desired letter. But it is evident that this method of using sound could not have extended to any great distance. His subsequent system of using the charged Leyden jar only required one wire, but the difficulty of keeping the charge to the wire would necessarily worry the inventor if he tried it over a distance. A very similar and better-known invention was Ronald's electric telegraph, in which the dials of the clocks moved round, bringing the letters of the alphabet painted upon them into view successively through an aperture in a covering case. When the desired letter appeared in the slot, a signal was sent by discharging a wire at the end of which a pair of electrified pith balls, suspended by two threads, repelled each other until the discharge took place, whereupon they immediately came together by gravity. By this primitive method the words of the message were slowly built up. After Volta's introduction of batteries, the idea of electric telegraphy became more practicable. While these two last-mentioned experiments were carried out with only one connecting wire, yet it was a long time before inventors could dismiss from their minds the idea that a reliable telegraph would require a great number of connecting wires. Even one of the greatest French scientists, Ampère, suggested an instrument which required as many as 30 connecting wires, and under the end of each there was to be placed a small magnetic needle. A few years later, a German professor proposed putting the 30 little magnets inside as many coils, instead of merely under the single wires. By this means, the effect of the current on the magnet was greater. An instrument of this kind was exhibited at the Royal Institution of London in 1830, in which telegraph 26 wires, coils, and magnets were used. It was several years before anyone suggested that one wire with a single coil and magnet would serve the purposes of signalling. To give even an abstract of all the early inventions in telegraphy would occupy a good deal of space, although every inventor who was bold enough to approach the government of his day regarding his invention received the somewhat discouraging reply that telegraphs of any kind other than those now in use are entirely unnecessary, as the government are fully satisfied with the semaphore system. How would the government of today feel if instead of the electric telegraph they had to be satisfied with sending intelligence by means of optical semaphores, as used from one ship to another at close quarters? End of Chapter 9.
Chapter 10 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Romance of Modern Electricity by Charles R. Gibson. Chapter 10. Telegraphing Through Space. An old-time swindler cornered by Galileo. Some interesting early experiments. Sir William Preece's method. How the present system is worked by Marconi and others. The importance of wireless telegraphy. Communicating with friends far out on the ocean. A wireless press news in America. The tuning of wireless instruments in order to obtain secrecy. Experience in the Russo-Japanese War. An exciting wireless incident. Noiseless wireless music. The idea of telegraphing to a distance without the aid of connecting wires is by no means a new one, although its practical accomplishment is within the memory of all. Some 300 years ago, a man claimed to be able to send wireless messages over a distance of thousands of miles by means of two simple magnetic needles pivoted on dials around which the letters of the alphabet were written. No matter at what distance the two dials were placed from each other, the inventor stated that he had only to move the one magnetic needle to point at any desired letter, whereupon the distant needle would immediately turn in sympathy to the corresponding letter on its dial. When the inventor was asked by the great Italian astronomer Galileo to show the instruments at work across his room, the adventurer said that when close together the magnets could not work. They required to be separated by a great distance before the one could influence the other. Galileo then suggested that the inventor should leave one instrument with him, take the other to any distance he desired, and then send him a message. But needless to say, this test was not convenient to the swindler. Other equally absurd proposals were made, and no doubt believed in by some, but it naturally was not till after the practical electric telegraph was in use that any genuine attempt at wireless telegraphy was made. Of the early experimenters, the most interesting is James Bowman Lindsay of Dundee, Scotland, who read a paper before the British Association in 1859 on, quote, telegraphing without wires, end quote. It is interesting to note that the illustrious Michael Faraday and our great scientist William Thomson, Lord Kelvin, were both present at this meeting. Lindsay was a great genius who lived for learning. He went to Dundee as a science lecturer in the Watt Institution, and later he acted as tutor and conducted private classes. While acting for 17 years as teacher in the Dundee prison on a salary of £50 per annum, he made many researches in electricity, constructing his own apparatus, and denying himself everything but the bare necessities of life to enable him to follow out his studies. In 1854, Lindsay took out a patent, quote, for transmitting telegraph messages by means of electricity or magnetism through and across water without submerged wires, the water being made available as the connecting and conducting medium. End quote. By such means, Lindsay sent telegraph messages across the Tay at a point where the river is about a mile in width. More recently, Sir William Preece worked out a method of wireless telegraphy on the principle that an electric current passing along one wire will, at each make and break of the current, set up a similar current in any other wire placed parallel to it, although the wires be placed miles apart from each other. The one drawback to this system is that the lengths of these two parallel wires have to be increased in proportion to the distance between them. Each wire must be about equal in length to the distance between the sending and receiving stations. It is apparent that on land, one might as well connect the two stations directly by wire, but this system has proved of service on more than one occasion where submarine cables have broken down, as between the English coast and the Isle of Wight, and between the mainland of Scotland and the island of Mull. If the distance from shore to shore be 5 miles, then a 5-mile line is run along each coast. The present method of wireless telegraphy, worked out by Signor Marconi, is more truly wireless, and is on quite a different principle. What Cook and Wheatstone did for the electric telegraph in Britain, and Morse in the United States, Marconi has done for wireless telegraphy. None of these inventors discovered the principles that made telegraphy possible, nor did they originate the ideas, but they brought known principles into practical form. When each country nowadays knows exactly what is happening in the other countries of the world, it would be surprising if the whole field of such an important matter as wireless telegraphy had been left to one worker. The following are some of the most prominent names in connection with wireless work: Marconi, De Forest, Fessenden, Lodge Muirhead, Popov, Jackson, Armstrong, Orling, Dolbear, Stone, Artem, Lepel, and Poulsen, etc. The general principle underlying all these systems may be easily understood. In ordinary telegraphy, the sender has beside him the battery and contact key, while the line wire conducts the current to the distant telegraph instrument. It will be remembered that the contact key is merely a small lever which, when depressed, closes the circuit and allows the current to flow from the battery to the telegraph line. An ordinary bell push would serve the purpose, though not so conveniently. Let us now imagine the whole of the apparatus to be placed at the receiving station, so that the battery with its contact key and the telegraph instrument are all connected up close together at the one place. If the would-be sender at the distant station could now, by any means, influence the contact key at the receiving station, making it close and open the battery circuit at will, he would then be able to operate the telegraph instrument and convey intelligible messages. It is, of course, quite impossible for the sender to operate the contact key, which is now far beyond his reach, but it is possible to substitute something in the place of the contact key, which can be influenced from a distance, even though the sender be hundreds of miles away from the telegraph apparatus he desires to control. At the receiving station, we now take away the ordinary contact key and replace it by a small tube or box of metal filings, so that the current will have to pass through the filings to get from the battery to the telegraph instrument. The filings are only very loosely packed together, and they offer so much resistance to the current that it cannot pass through them. This little tube, with the filings in their normal condition, is equivalent to the ordinary contact key when open. These filings are, along with every existing thing, immersed in the great ocean of ether which pervades all space. We shall become more familiar with this all-pervading medium in a later chapter. For the present, we shall be content to know that it is waves in this great medium which provide the connecting link between the transmitter and the distant receiver in wireless telegraphy. It is a marvelous fact that if certain ether or electric waves fall upon these little metal filings, their electrical resistance to the current is so far diminished that the current is able to pass through them and operate the telegraph instrument. The tube is then shaken, the filings return once more to their ordinary condition, and no current can pass. It will be observed that in this action we have an equivalent of the ordinary telegraph contact key, which may be closed and opened at will. It only remains to produce the necessary electric waves to operate it from a distance. An ordinary electric spark produces waves in the surrounding ether, but a feeble spark can only give a small result. By means of what is known as an induction coil, we can so increase the pressure of an electric current that it will leap across an air gap, and in doing so it will produce a perfect torrent of sparks. Owing to this electrical discharge, the surrounding ether is disturbed, and waves travel out in all directions. It is remarkable the distance at which these waves may be detected by the little tube of filings already described. In seeking to describe the function of these filings, they were said to cohere together when the ether waves fell upon them, and from this description the tube became known as the coherer. We may picture the operator at the sending station switching the current on and off from the induction coil, producing torrents of sparks at will. He knows that each time he does so, ether waves will reach the distant receiver and cause the telegraph instrument to record the signal. If the sender wishes to signal the Morse code, he will arrange the duration of his spark torrents accordingly. 3 sharp torrents following close at each other's heels will record the Morse signal for the letter S. All the other signals which are detailed in Figure 4, page 57, may be signaled in the same way. As the coherer tube is a very small thing, it is connected by wires to metal arms, or capacities, which intercept the ether waves and conduct the electromagnetic effect to the filings in the small tube. It will be understood that the simple apparatus which I have described is descriptive merely of the general principle of wireless telegraphy. One can get very good results with such apparatus over a very short distance. For long distances, we require a more powerful disturber of the ether and a more delicate detector at the distant receiving station. For distances up to about 200 miles, a storage battery and an induction coil can produce sufficient disturbance in the ether. To send messages to greater distances necessitates the wireless station being equipped with an engine and dynamo for generating the necessary electric currents with which to set up the ether waves. The receiver may be some form of delicate coherer or anti-coherer. This latter term signifies that the receiver does not require to be tapped or shaken after each impulse. Another form of detector is based upon electrochemical changes which take place in the receiver when the ether waves arrive. Those in this class are called electrolytic detectors, while they might be described also as anti-coherers. One such device is composed of a small tube similarly arranged to the ordinary filings tube, but with 2 little blocks or rods of tin, between which there is placed a semi-liquid paste, sometimes composed of alcohol with tin filings and lead oxide. The operation of this tube is exactly the reverse of that of the metal filings tube. It will be remembered that when the ether waves arrived, they enabled the filings to close the local battery circuit. In the electrolytic detector, the arrival of the ether waves stops a current which is kept flowing through the detector. The chemical paste in its normal condition permits the battery current to get across from the one tin block to the other, but the stimulation of the ether waves produces a chemical action which immediately breaks down this bridge and stops the current. Upon the withdrawal of the ether waves, the paste returns at once to its normal condition and allows the battery current to pass again. The signals are therefore a sudden breaking and making of the battery circuit. How can these signals be read? If a telephone receiver is connected to the tube and battery, it will be very easy to tell when the battery circuit is broken. There will be quite a loud click heard in the telephone. Any person using the ordinary telephone may hear a similar click by depressing the telephone hook, or support, while the receiver is held to the ear. Each time the support is depressed, the battery current is cut off from the telephone, and it is the stopping of the current causing a sudden change in the magnetic field of the receiver which produces the click. This makes quite a good demonstration of how the wireless messages are read. Then there are magnetic detectors, in which we depend upon the incoming ether waves affecting a piece of magnetized soft iron. The general principle of these will be understood if we picture an endless band of soft iron wire kept in motion so that bit by bit the wire passes close to the poles of a permanent magnet. The magnetism of the wire tends to change as it passes from the influence of one pole to the other. It was discovered that the time required for this change was very greatly reduced when ether or electric waves fell upon the soft iron band. The magnetic change is thus rendered so sudden that it is capable of inducing a momentary electric current in a coil of wire through which it passes. This induced current is detected by a telephone receiver which is included in the circuit. The signals of the Morse code may be read easily by such means. The operator in the photograph facing page 94 is reading wireless signals by means of the telephone receiver, which is attached to his head so that he may have the free use of his hands. There are many other interesting devices for detecting the arrival of the ether waves, but sufficient detail has been given to enable the reader to understand the general principles. At all wireless stations there is some metallic arrangement extending up into the air to entrap the ether waves. Such arrangements are called antennae. Those of us who spent some of our boyhood leisure hours in collecting beetles and other insects will find this word a familiar one. It is the name of those little horns or feelers extending from the head of the insect. With this picture in one's mind, one can see the appropriateness of the word as used in wireless telegraphy. One method is to erect a simple wire on a pole. In another, a whole network of wires is supported from strong steel towers built to a height of over 200 feet. Sometimes the wires have been arranged like a great inverted pyramid, while one system employs a huge sheet iron tube, not unlike a factory chimney, reaching a height of over 400 feet. Some of the most recent transmitters do not disturb the ether by means of torrents of sparks. They employ a very rapid to and fro, or alternating current, to set up the necessary ether waves. This method has been found much more economical in the power required for a given range of communication, besides having other advantages. In the first days of wireless telegraphy, we used to employ the picture of two men shouting to each other across a distance as being analogous to two wireless telegraph instruments, while two persons using an ordinary air telephone or speaking tube represented two ordinary telegraph instruments connected via a wire. The simple analogy of two men shouting always suggested the possibility of some third party being within range to hear the communication. Then again, one knows the difficulties arising from a number of people all shouting at the one time. Similar difficulties were bound to present themselves to the wireless telegraphists when they began to multiply the number of their installations. From the outset, we heard a good deal about the interference and interception of messages. One ship would even pick up a message sent out by some rival system of wireless telegraphy. This formed the most serious problem that the wireless telegraphist had to face. That very considerable success in overcoming this difficulty has been made is demonstrated by the following facts. One of our battleships was communicating by wireless telegraph to another ship of war distant from it about 500 miles. While this signaling was in progress, another wireless instrument on board the same battleship was receiving messages from a third vessel within close range. How can this be done? The instruments are, quote, tuned, end quote, so that they respond to each other. There is an experiment with tuning forks which gives us a suitable analogy. The airwaves, sound, from one tuning fork will cause a second fork of the same pitch to vibrate also. Unless the two forks are tuned to the same pitch, the one will not respond to the other. We need not trouble with the details of electrical tuning, except to point out that the transmitter has to be arranged to send out a definite rate of ether waves, while the receiver is arranged to respond to that same rate of vibration. In these days, when wireless telegraphy has an established position, it is hardly necessary to point out its great value. We may debate the probability of wireless competing with ordinary telegraphy on land, or whether it will ever enter into serious competition with ocean cables. We cannot, however, fail to see the very wide field which wireless telegraphy has entirely to itself. It has no rivals in communicating with ships far out at sea. It is impossible to overestimate the value of this. In addition to the communication of ordinary intelligence, there is the possibility of a ship in distress being able to call for help from those who cannot see her. It is difficult to realize what it would be to find ourselves drifting helplessly out of the track of steamers, where it would be impossible to attract attention to our disabled ship. Or picture the crew upon a sinking steamer, unable to call for any assistance. We have had some very remarkable instances of large vessels sinking, and the wireless operator succeeding in calling the help of other steamers, to which it would have been impossible to signal by any other known means. Indeed, one has only to read the daily papers to be impressed with the great importance of being able to signal through space without the necessity of connecting wires. That wireless telegraphy is likely to prove of value in warfare is appreciated thoroughly by both military and naval authorities. The old proverb that to be forewarned is to be forearmed still holds good. It is obvious that the earlier we can learn the whereabouts of the enemy, the more chance we have of dealing with them to advantage. End of Chapter 10.
Chapter 11 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2022. The Romance of Modern Electricity by Charles R. Gibson. Chapter 11. Electricity in Nature. Franklin handles the lightning. A Russian professor accidentally electrocuted at St. Petersburg. Different kinds of lightning. A false notion. Thunder raindrops explained. How we may imitate the Swiss mountain air in our hospitals. The Aurora Borealis and magnetic storms. Wonderful electric fish. Earthquakes and volcanoes. From the earliest ages, man has been familiar with the lightnings and thunders of the heavens, but if anyone had dared to predict that these grand phenomena would be found to be due to the same source as that exhibited by rubbed amber, such a prophecy would have been deemed beyond all reason. Although primitive electrical machines were constructed about the middle of the 17th century, it was some 50 years later before experimenters suggested that lightning was simply an immense electric spark, and it was not till some 40 years after these suggestions were made that Benjamin Franklin, one of America's greatest men, was able to prove this to be a fact by drawing electricity from a passing thundercloud by means of a conductor carried upwards by a kite to make communication with the cloud. Using a metal key at the lower extremity of the wetted string, which acted as the conductor from the upper atmosphere, Franklin was able to perform all the known electrical experiments by charging bodies from this key. Franklin had made known his intention of carrying out such experiments, and news of these particulars having reached France, the experiments were there successfully carried out prior to Franklin's demonstration in America. When Franklin had succeeded in drawing an electric charge from a thundercloud, it occurred to him that it would be possible to rob these clouds of their charges and thus prevent them discharging to earth through high towers, etc., which were so often seriously damaged when struck by lightning. In this way, we came to have lightning conductors attached to high buildings. It is amusing to read that at that time, the summer of 1756, a German scientist prevailed upon a clergyman to have a lightning conductor erected at his house, but it so happened that this summer was a very dry one, and the peasants, believing that this lightning conductor was the cause of their trouble, made so much noise about the matter that the reverend gentleman had to remove it. The danger incurred by any person receiving a violent shock from a conductor drawing electricity from the clouds was not appreciated, and a Russian professor at St. Petersburg, having erected an insulated iron rod leading into his house with the object of studying atmospheric electricity thus collected, received during a thunderstorm such a shock that he was killed instantaneously. This victim to scientific research, Professor Richman, had omitted to provide any connection whereby the electricity might have passed harmlessly to earth. We now know that lightning is merely a sudden discharge of electricity from one cloud to another, or from a cloud to the earth, in every way similar to the discharge between the inner and outer coatings of a Leyden jar, but on an immensely grand scale. The noise of this great discharge becomes a mighty roar as it echoes through the clouds. The quantity of electricity in a lightning flash is extremely small, but it is at a tremendous pressure. Here we have electricity leaping a great distance from a cloud to the earth, across the intervening air space measuring sometimes a mile in distance, and yet we should require a battery of 1,000 cells or more to make the current jump over an interval of 1/1000th of an inch of air space. Lightning without thunder is sometimes merely the reflection of a far distant thunderstorm, or at other times it may be a quiet discharge from one cloud to another, where the difference of potential is not very great. If the thunder quickly follows the lightning, we know that the discharge is taking place very close at hand. I can remember, when a youngster, being so close to a lightning discharge that the flash and noise seemed simultaneous. I felt a sudden contraction of the muscles, and I could plainly smell the ozone or electrified oxygen. On this occasion a building within a stone's throw was struck by the lightning. It is possible to roughly calculate the distance one is from a thunderstorm by timing the interval between seeing the flash and hearing its thunder. The light is seen practically at the moment of discharge, for light waves in the ether would travel 8 times round and round the earth in 1 second, but the sound, or air vibrations, will only travel at about 1,100 feet per second, so if the number of seconds between the lightning and thunder are noted, a simple calculation will give the distance the sound has had to travel. If 15 seconds elapse, then the distance will be a little over 3 miles. We can recognize 3 different kinds of lightning: fork lightning, sheet lightning, and ball lightning. In fork lightning we have a greater disruption than in sheet lightning. The latter appears as a slower discharge, although the whole time in which any electrical discharge takes place is a very small fraction of a second. Ball lightning is rare, and has the appearance of balls of fire bursting in the air with a loud explosion. It is very amusing sometimes to read in the daily press the graphic account of a building struck by lightning. I recollect one report reading like this: "The lightning entered the building by the chimney, rushed across the floor, and making its way to the lower part of the house by the gas pipes, it forced a passage through a crevice," and so on, And yet all this took place within one tiny fraction of a second. The disruptive effects of a lightning discharge into the earth have sometimes been so great as to give rise to the belief that a material thunderbolt had been shot into the earth. If we force a very fine jet of water up into the air so that it falls in such fine drops as to be little more than a mist, and if while this is happening we electrify a vulcanite rock by simply rubbing it with a cat's skin, and bring this small electrical charge near to the fine stream of water particles, they become electrified, and uniting together they form quite large drops. This experiment is a very good representation of the heavy rain accompanying a thunderstorm. One often feels a decided heaviness or want of life in the atmosphere immediately before a thunderstorm, but as soon as the storm is over, the oxygen of the air seems to have gained renewed vigor. It is well known to all that great benefit is derived from the high mountain air of Switzerland by patients whose breathing apparatus is defective. On these mountain tops we find a large quantity of ozone or electrified oxygen, and in addition the air is free from a good deal of both the organic and inorganic matter to be found in the vicinity of cities, while the air being dry and cold, its dust particles are easily repelled from the heated surfaces of the lungs. Some 12 years ago I made the suggestion, through a medical friend, to the staff of one of our hospitals, that in a ward with patients suffering from diseased or weak lungs, an apparatus might be arranged to alter very considerably the conditions of the air, and bring these nearer to those existing on the Swiss and other mountain tops. I proposed that the air should first of all be cleaned by filtering through glass wool, etc., and that it should be dried and then cooled to a convenient temperature, while some additional oxygen might be added if desired, and then finally passed through a large vulcanite chamber in which some high-frequency machines would be kept discharging for the production of ozone, and the air in this altered condition might be led into the ward through vulcanite tubes and distributed at the patients' bedsides. The suggestion met with some approval, and I was offered facilities to carry out experiments, but not being connected either with the electrical industry or with medical practice, I merely offered the suggestion that those specially interested might make the experiment, the result of which seemed to me a foregone conclusion. Nothing was done, but I have been interested to note of late that the same idea has been carried out in other quarters. In contrast with the terrorizing lightning, we have the beautifully peaceful display of the Aurora Borealis. While this exquisite phenomenon is not of very frequent occurrence in our latitude, it may be seen nightly in the polar regions, but never at the equator. This beautifully luminous effect occurs in the heavens at both poles of the earth, but that at the south pole is termed Aurora Australis. Franklin explained these phenomena as due to discharges of electricity through rarefied air, such as we see on a small scale inside a vacuum tube. The magnetism of the earth is disturbed in the neighborhood of these displays, and we have what are termed magnetic storms. In a telephone having an earth return, instead of a complete metallic circuit, strange sounds may often be heard in the stillness of the night, due to earth currents possibly set up through the medium of the ether by some disturbances in the sun. The whole telegraphic circuits of this country are occasionally completely upset by these magnetic storms. Electrical phenomena have long been known to exist in the animal world. Indeed, one of the earliest electrical observations was that of certain fish being able to deal out startling shocks. This fact is recorded by the greatest of ancient philosophers, Aristotle, more than 300 years before the Christian era. We also have some interesting details noted by Pliny, who lived early in the 1st century of the Christian era, and who lost his life by suffocation from the fumes of the great eruption of Mount Vesuvius, on landing to witness the great phenomenon. Pliny records the fact that when the torpedo, an electric fish found in the Mediterranean, was touched with a spear, it paralyzes the muscles and arrests the feet, however swift. Then we have the ancient record, mentioned later in chapter 23, of a man having been cured of gout by the shock from one of these torpedo fish. Although these properties were known for such a very long time, it was not till late in the 17th century that modern naturalists gave the matter any serious attention. It was only then that this shock was recognized as being of electrical origin. Our present knowledge includes some 50 different kinds of fishes which show electrical properties, but the best known are the electric eel, Gymnotus, and the electric ray, Torpedo galvani. The Gymnotus, which measures 5 or 6 feet in length, is said to be able to deal out a shock sufficient to kill a man. Many experiments have been successfully performed with the electricity derived from these fish, such as the lighting of an incandescent lamp, the magnetizing of needles, and the decomposition of water. This electrical property has doubtless been bestowed upon the fishes as a means of preying upon smaller fish for food, and probably also as an active means of self-defense against greater monsters. There still remains a great deal of uncertainty as to the nature of the production of these shocks. With the advent of delicate electrical tests, it was found that in our own bodies there are continual electrical changes taking place on a small scale. Earthquakes, although experienced from ancient times, have received little scientific attention until quite recently, and even now little is really known as to their origin. One great astronomer has asked us to imagine the solid crust of the earth to be no thicker in comparison with its molten contents than an eggshell is to its yolk. We are then to suppose an earthquake to be due to the cooling down and consequent shrinkage of the molten center and the necessary taking in of the outer coating to adjust itself to the new condition, as an older brother's suit or clothes might be cut down to fit a younger brother. Other physicists argue that the earth is solid throughout, and that there is no fusion, although the internal temperature is enormous. The reason why it may be at a very high temperature and yet not fuse or melt is that the materials are under great pressure, and if a body is subjected to a great increase in pressure, it requires a very much higher temperature to fuse it. This view suggests that the molten effusions from volcanoes are merely local and do not necessarily prove that the Earth's center is molten. If a body that would melt on the Earth's surface at, say, 1000 degrees be subjected in the bowels of the Earth to such a pressure that, although it is there at a temperature of 2000 degrees, it does not melt, and if the pressure be suddenly removed or relieved by some disturbance elsewhere, the heat it contains will instantly liquefy it. Whatever may be the true cause, for there will certainly not be only one cause operating, the great material disturbance is bound to give rise to an alteration in electrical conditions in the earth, but my present purpose in referring to the subject of earthquakes here is in connection with the recording of such disturbances by electrical apparatus as will be described in a later chapter. End of chapter 11.
Chapter 12 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Amelie Dawson. The Romance of Modern Electricity by Charles R. Gibson. Chapter 12. Interesting Applications of Electricity. What makes the electric bell ring? How indicators work? An alarm clock that will insist on its victim rising, automatic fire alarms, a room automatically kept at an even temperature, a burglar that knew too much and yet not enough, the block system on railways. In addition to the principal applications of electricity separately dealt with in the various chapters, there are manifold other uses in everyday life to which this willing servant may be put. Perhaps the commonest is the electric bell, which alone covers a wide field. Its principle is very simple and its operation interesting, and yet how many possessors of these bells have ever taken the trouble to lift off the outer case to see how the bell works? Under normal conditions, the electricity cannot get from the battery to the bell because the connecting wire is purposely broken at the push on the wall, but when anyone presses the button of the push, the two ends of the wire are pressed together and the current gets through and rings the bell. The current passes round an electromagnet, causing it to attract a lever towards it, and on the end of this lever is a gong stick, which thus coming quickly forward strikes the bell or gong. This will, of course, only make one stroke each time you send the current through by pressing the button, so bells of this kind are called single-stroke bells and are used for signaling on tramway cars and for many other purposes, but when you wish to call the attention of a servant you prefer to have something a little more vigorous in its action. With the single-stroke bell you could easily make a series of blows upon the gong by repeatedly pressing and releasing the push alternately. But this proceeding would be rather tiresome, so the bell is arranged to do this making and breaking of the circuit for you. Instead of leading the current directly to the electromagnet, the wire is attached to a little pillar, against which the gong stick leans when at rest, and the current must pass up this pillar and thence through the gong stick to the wire of the electromagnet. As soon as the push is pressed, the current gets through from the pillar to the magnet, which immediately attracts the gong stick forward against the gong. But as the gong stick is no longer touching the pillar through which the